Yesterday we looked at charges that were accelerating in electric fields, and I told you essentially that whenever you get a charged particle that's speeding up in an electric field, I want you to think of it as a car going down the hill. Yesterday we drew that analogy. Car was at the top of a hill. It had a speed of, let's say, 20 meters per second. The hill had a height of maybe 30 meters. And maybe we wanted to find the speed of that car halfway down the hill. What kind of energy would that car have at the top of the hill? It's got potential energy, which is mgh, right? Is there anything else? Yeah, it's got kinetic energy as well because it's moving at the top of the hill. Now, what happens as it goes down the hill? Does it gain potential energy? Does it lose potential energy? It loses potential energy. Does it gain kinetic or lose kinetic? It gains kinetic. What about the total energy? The total energy will stay the same. Now, what kind of energy do we have when it's halfway down now that it's lost some potential and gained some kinetic? It's still going to have both. We certainly know it's going to have kinetic because it's gained kinetic, but we haven't gone all the way down to the bottom of the hill, so we are still going to have some potential energy. It's going to be mgh. Now, if we've got a situation where we've got a charged particle between two parallel plates, let's make this the positive plate, this the negative plate. Let's put a positive particle in there with an initial speed of, say, 20 meters per second. And not a distance between the plates, but rather a potential difference between the plates of 30 meters, so 30 volts, I should say. Then we would analyze this in the same way. We would picture this as being a car going down a hill, because of course that positive particle is going to accelerate or speed up as it goes away from the positive, gets repelled by the positive, and attracted to the negative. So picture it. Like, picture the car at the top of the hill moving. Like, picture the details of the car. You can see this. You can't see an electron that's accelerating. We have a tough time visualizing that because we don't really know what an electron looks like. But we can visualize the car at the top of the hill. And when we do that, we would say that, well, the car has, at the top of the hill, potential energy. The car has kinetic. And then when it goes halfway down the hill or halfway across that gap, it has potential and kinetic energy again. The only difference between that first question and this question is what? Yeah, the potential energy is not mgh potential energy. The potential energy is Q times V. This would be QVI, this would be QVF. Is that a little v or a big V? That's a big V. Little v means speed, big V means potential, or delta V means potential difference. So we sub our numbers in, we solve for what we're looking for, probably VF in that case. Make sense? All right. Well, what if we have a situation where you don't have a car going down the hill, but rather you got a car going up the hill? It's a pretty steep hill, but it's a pretty good car. This car has a speed of 20 meters per second. Car's going up the hill. Let's assume that this car does make it all the way to the top of the hill and is still moving when it gets to the top of the hill, okay? It might not. Maybe it doesn't make it all the way up, but let's assume that it does. What kind of energy does it start with at the bottom of that hill? Yeah, it starts with kinetic energy. It has to. You can't make it up the hill if you don't have kinetic energy to start. Does it have potential at the start? No. When it gets to the top of the hill and is still moving, does it still have kinetic energy? Because it's moving. Now, you may have a situation where it just barely makes it to the top and it's not moving, and then there would be no kinetic. But in this case, there's a final kinetic energy. What happens when it reaches the top in terms of potential? Does it have potential now? Yeah, sure, it has potential to fall back down to the bottom of the hill. So we'd say it would be mgh. All right, let's look at that situation again where we have the charged particle. Positive plate, negative plate. This time, let's make the positive over here with an initial speed to the left of 20 meters per second, or whatever. What's going to happen to that positive particle? Is it going to speed up or slow down? As it's moving toward the positive. As the positive moves toward the positive, it will slow down. That's like a car going up the hill. So visualize it as a car going up the hill. Visualize the details of the car going up the hill, and then identify what kind of energy you have at the bottom and at the top of the hill. If we do that, we're going to find we get exactly the same thing as we had over here. But kinetic energy at the first plate or the negative plate, or we call it the bottom of the hill. And then at the other plate, assuming it's still moving, assuming it hasn't stopped, we'd say that it has both kinetic and potential energy. Except that we'd replace gravitational potential energy with electric potential, good, which is what equation? Yeah, VQ, or you could say Q times V. It doesn't really matter. Make sure you make it a big V, though, so you can distinguish it between speed and electric potential. We solve the problem exactly the same way as we'd solve the problem over here, except that we've got QV instead of MGH. Telling you, you might think that, like, oh, I don't need to do that. I'm fine with the QV and the 1/2 mv squared and so on. You know what? You might be okay. You might be okay without visualizing it as a car going up the hill and down the hill. But I'll tell you, in my experience, and I've got quite a bit of it, most people do better if they can see it, if they can visualize it, right? We can visualize a car. We can't visualize, not nearly as easily at least, an electron that's speeding up or slowing down. So in my experience, it is easier to picture this as the car going up the hill and do everything as if the car is going up the hill and then just sub in QV for MGH. Now, I'm not saying that necessarily, hold on one sec. I'm not saying necessarily you should necessarily write out MGH literally and then erase it and put in QV. You might be able to do that substitution in your head, okay, but you should picture it that way. Does that make sense? All right, you do have a little bit of homework tonight. You thought you were getting away with it because the bell just went, but you do have worksheet number 9. Worksheet number 9. And it's questions 1 to 4 and 6. 1, 2, 3, 4, and 6 on worksheet number 9.